Thank you, Mr. Chairman, for your kind introduction. I'm very happy to be able to talk to you today. My name is Yuto Morita, and I'm a student at Kagawa University in Japan. Today, I'd like to talk about the method for measuring and evaluating for moist feeding. Okay, I'll start the introduction. The human fingertips are very delicate, and there are many words to describe this sensation. In recent years, it has become increasingly important to establish evaluation method for tactile sensation. Accordingly, the development of tactile sensors with the capabilities of human fingertips is required. Most previous tactile sensors have been developed mainly for force sensors, but their resolution is limited and does not reach the capabilities of human fingertips. In contrast, our high-resolution tactile sensor can acquire tactile information with higher force resolution and a spatial resolution than fingertip skin. In addition, clear methods have been established for rawness, hardness, warmness, and friction by our sensor. On the other hand, for moistness, characterized so-called moistness, the perception mechanism is still unknown, and no effective measurement method has been established. In this presentation, we report on method of measuring and evaluating moist feeding by our tactile sensor. In the next slide, I'll introduce the method. First, we describe the tactile sensor we have developed. This figure shows our tactile sensor, and the suspension deforms and directs forces in the two directions. And by pressing sensor against the object and scanning it, the load force and friction force can be acquired. And these measured values are used to evaluation. So, in this section, I'm going to talk about the perception mechanism of moistness. We focus our research on the friction force on fingertip skin. There are two main possible modes of friction. The first is a general friction that is proportional to the vertical load. And the second is an adsorptive friction due to surface energy and surface tension. And we expected that the absorption friction would be the most important factor in the perception of moistness. The model of interfaces with and without water are shown. In the absence of water, the surface tension of the water acts as an absorption force. And even in the absence of water, the surface energy as an interface may act as an absorption force. This absorption force is similar to the water, makes human feel moistness. So we present a simplified friction model to consider this adsorption friction. This figure shows the friction force against the load force. On dry surfaces, the friction force is basically proportional to the vertical load force, and the coefficient of friction is near constant. On the other hand, on a surface that feels moist, the surface adsorption force acts, and the friction force will be active even if the load is near zero. And this slide shows a method for evaluating the moist feeding using the friction model. Here, the A is the coefficient of friction and B is the adsorption force generated by the surface energy. The degree to which surface adsorption force is dominant over the normal friction is expected to affect the moisture sensation. So, the important ratio B over A is a feature value that evaluates the moist feeding with or without surface water, and can be used to quantify the moist feeding. And this section describes how to evaluate the moist feeding. And first, the vertical load and friction force are measured by pressing the sensor and against the object. At this time, the contactor moves vertically along the shape. The measurement is taken with the load range kept so that a scalar plot can be created. Then a regression line can be calculated from the scalar plot. The regression lines are used to determine the A and B for the future values. As a flow, first measurements are taken and second scalar plot and regression line are calculated. And finally, the feature values are obtained and evaluated. So, based on the above evaluation method and measurement techniques, we conduct a measurement experiment. There are two groups of samples used in this experiment. The first group consists of dry and wet cotton and rayon. In addition, dry paper and artificial leather. These samples each have a clear difference in tactile feeling. The second is a closed material, blanket with a controlled water content. The water content and the feature values are compared. And the result of the evaluation of the feature B over A are shown. And there is a clear difference between samples that feel dry and that feel moist. This result indicates a difference in the moist feeling between each sample. And the method enables an evaluation of moist feeling. However, this method has one problem. The figure shows the scalar plot actually measured on closed and resin material. For the closed material, the regression line can be correctly calculated from the scalar plot. On the other hand, for the resin material, the range of the scalar plot is limited. The range of load force is acquired by the vertical movement of the contactor during scanning. And if the surface of the sample has some roughness, the contactor moves vertically and can be measured at certain range of vertical load. But the surface of the resin material is flat, and the range of vertical load change is limited. And therefore, it is not appropriate to calculate the regression line from the obtained scalar plot. And sensing is not possible for flat samples such as resin material. And to solve these problems, a new sensor method was considered. In order to solve the problem, a tactile sensor with arrayed multiple contactor is used in this study. The arrayed tactile sensor is composed of 3 different types of contactors with different amount of protrusion. Therefore, each contactor is able to take charge of the different load level and extend the vertical load range. Thus, it is easier to obtain friction over a wide range of vertical load, and a scalar plot is suitable for calculating regression line. Using array tactile sensor to solve problem and measure tactile sensation, we conduct experiment for urethane resin. This urethane is viscous and feel moist even without water. And the urethane sample are scored by the actual human and ranked in degree of moistness. Importantly, there are the same material with different moistness and ranked despite the absence of water. First, a scalar diagram measured by array tactile sensor. The vertical load range has been extended and regression line is correctly calculated from a scalar plot. These results indicate that the material with flat surfaces can be accurately measured. And finally, the next slide evaluates the moistness. The figure compares the feature values of moistness. The feature values on the vertical axis and the sensory evaluation values on the horizontal axis. The overall result shows that there is a clear there is a positive correlation between the sensory evaluation values of moistness and feature values. Importantly, there is a positive correlation between the values by the sensors and the values perceived by humans. And the tactile sensation were able to produce the sense of touch in terms of feeling. Finally, I'd like to conclude my presentation. In this study, we proposed a new hypothesis for the perception of moistness. Based on the hypothesis, features were selected and we have succeeded in clearly extracting the difference in moist feeling with or without water. The load range was extended to provide a suitable evaluation for moistness. And the tactile sensors were able to produce the sense of touch in terms of moist feeling. Okay, that's all. Kind of for your attention.
Thank you.
Thank you.